So first of all, thanks to the organizers for pulling up this. It's almost like a very big workshop. And secondly, I'm very thankful to the audience here as well as those who are still tagging along to the very last phase of the workshop. Okay, so having said that, I would first like to acknowledge the contribution from my student Shaujanna Datta, who might be here in the audience, who is the main driving force behind this work. Okay, so you will find the details of this work in this preprint. And as the title suggests, I will be talking about some anomaly associated with Landau levels, which we all know from our maybe quantum mechanics 101 or 102. And then I will talk about what will happen to those anomalous levels when we, instead of homogeneous magnetic field, which we typically apply to understand Landau levels, we make inhomogeneous magnetic fields. Okay, good. So I think practically some of my first slides may not make much sense, in the sense that you are already very much familiar to these things. We all are very much familiar with the quantized motion of electrons under the magnetic field that has led to the development of this phenomena called quantum Hall effect. And the discovery of quantum Hall effect has basically launched the program of topological quantum matter. Okay? Among many of the applications of quantum Hall, one is to set the current resistance standard, and it's used in precision metrology. So what's behind this quantum Hall effect? So we know that the physics comes from the quantizations of the electronics orbits that also manifest in the energy quantization. So in the presence of the magnetic field, you have quantized levels, okay? And these quantized levels are very similar to the quantization that we learn in quantum harmonic oscillator in quantum mechanics. These levels are isospaced. So basically spacing between two consecutive levels are same. Okay? So this is the regular notion of Landau levels that we all are familiar about. Now whatever I discussed in the first slide, that basically apply to non-relativistic particles, but you can be more imaginative. You can apply the construction to relativistic particles also. And since the discovery of graphene, people have put extensive effort in understanding this kind of appearance of Landau levels for relativistic particles. And what they found is rather remarkable. They found that the tower of the Landau levels are very different than the corresponding non-relativistic counterpart. And what you find particularly, that the scaling of the Landau level that was previously, I'm not sure if I showed to you, it was previously E goes as n plus half, which is the usual ladder spectrum for the quantum harmonic oscillator. For graphene, it becomes E goes as plus minus square root of n. This plus minus square root of n comes from the chiral symmetry present in the system. And you also have slightly different Hall quantization condition. Okay? But in any case, I mean, if I try to understand the different types of Landau levels that you have in relativistic as well as non-relativistic settings, I can put them up under one umbrella, which is known as Onsager semi-classical quantizations. Okay? We might have all learned about these Einstein-Brillouin-Keller quantizations in phase space, also known as Sommerfeld quantizations, and from that Onsager derived quantizations in the momentum space. And what you can see, that basically the area of the orbits in the momentum space is quantized, okay, up to the scaling factor of LB square. Okay. So the second term here is an extremely important term, which was not there during Onsager's time. It was later discovered, and this plays the role of Berry phase. Sometimes you can systematically expand this in terms of magnetic fields. Then it will include contributions of orbital magnetization, susceptibility, etc. Okay? But importantly, the take home is that you have a quantization, Onsager quantization, and once you know the dispersion relation of E as a function of K, you can also predict the dispersion of the you can also predict the quantization of the Landau levels in those dispersive systems. So for example, if you have a dispersion of the form E goes as k to the b, then the corresponding Landau level quantizations will go as En scaling as n to the b over 2. So if you just set b equal to 1, you get the graphene results back, and if you get b equal to 2, which is a regular dispersions, you get the usual Landau levels. Okay, good. But then we ask the questions. Of course, we understand that as long as you have dispersions, there will be Landau levels. Okay, and the parameters from the dispersions will basically dictate the scaling of the Landau levels. Okay, but then you can certainly ask the question: what happens if you do not have the intrinsic scales associated with the band structures? Okay, so for example, for a quadratic band structure, you have inverse mass, which gives you the prefactor in the Landau level quantizations. For Dirac, you have Fermi velocity that dictates the Landau level quantizations. So these are all intrinsic parameters of the band structures, and we ask that what happens if you do not have any intrinsic parameters associated with the band structures. Okay, I think by now you have probably understood where I am going to. Essentially, I am coming to the scenario of flat bands, which have no parameters as such to say, except for the position of the flat band in the energy landscape, and we ask that what happens to the Landau levels when you have flat bands, because in the absence of dispersion, I am not in a position to apply this quantization condition. So I ask the question, should I expect any quantized Landau levels when I have flat bands? Okay, that's the question that I pose, and for the rest of the talk, I will essentially be analyzing what happens, okay, to this thing. Okay, so these are some examples of flat bands. I think all of you know that a trivial manifestation is the atomic limit that you have learned in solid state 101, and however, you can have flat bands even in dispersive system because of the interplay of the geometry or the lattice geometry particularly. For example, you can have a flat band in these 1D systems. This is a sawtooth ladder where you can have a gapped flat band, basically, this flat band which is completely gapped from the rest of the spectrum, okay. And for some of these flat bands, you can probably tune it to the atomic limit also. And a more interesting scenario appears in 2D systems, okay. Particularly, this is known as a Kagome lattice, where you can have a gapless flat bands, okay. You have a gapless flat band, and there is gapless flat band is touching another quadratic dispersive band, which you can probably see here. Good. So these are the basic structure of the flat band, but there are some very intriguing features associated with the flat band that appears in the dispersive systems compared to the atomic limit. Okay. So let me explain that. The name of the phenomena is called compact localizations. Let me be very brief in explaining that. You can write down any single particle state. Okay. The spatial form of the single particle state will be of this form. That we all know from the tight binding model calculations. Okay. So you can see that this is the spatial part of the say single particle state, and this is the corresponding block part, okay, that I am doing this Fourier transformation to get this. Now it turns out that these compact localizations that I am going to tell you in a moment happens when you have a very spatial property satisfied by these elements which you get from the diagonalization of the block Hamiltonian. Okay. So what happens is that when these quantities that you get from the eigenvectors, so the block eigenvectors, admit this kind of Laurent polynomial structure or a finite sum of block phases, you get to see that there will be localizations of the real part of the wave function within a cluster of the sites in the lattice. Okay. So that is what happens for the flat band. If you look at the real space structure of the eigenstate associated with the flat band, you will see that that is localized on a cluster of sites which is sort of more than the Wannier orbitals. Okay, it's a collection of few Wannier orbitals. Okay, so this phenomena is called compact localizations. So basically, what happens is that your electron cannot, because of the structure of the wave function, when you map it to the real space, the electron cannot leak to the nearby sites. Okay, so for example, you can see a structure of the wave function here. The corresponding amplitudes are +1, -1, +1, -1s like that. Because of that, you can see the wave function cannot leak to this yellow point because it will receive the contributions, equal contribution from both the sides that will cancel each other. Okay, So there will be a destructive interference in the system for which you get localized states for the flat band. There is a very different type of localizations that we typically study in the presence of disorder. Okay, very good. So now these phenomena of compact localizations, you can ask the question that given a flat band, should I always expect an equal number of compact localized states which is equal to the number of states that you have in the flat band? Okay. Now it turns out this question intrigues a very beautiful classification of gapless flat bands, and the classification is simple. If you have a gapless flat bands, it is not guaranteed, suppose you have n number of states in the flat band, it is not guaranteed that you will have an n number of independent, linearly independent compact localized states. Okay. So there are two scenarios, in one case you can get and the other case you will not be able to get that. Okay. So think of this flat band, and based on this feature that I just mentioned, I can decompose the set of flat bands, the set of gapless flat bands into two broad classes. One I call a non-singular flat band, okay, and the other I call a singular flat band. So for the non-singular flat band, you can actually write down a complete set of compact localized states. For the non-singular flat band, it turns out if you want to write down the complete set of compact localized states, at least one of them will have some extension along one direction. Okay. Maybe I can briefly show, I am not sure if it is visible here, maybe not, okay, then I do not have it in here, but okay, take my words for now. So I have two different classes of flat bands, one is called singular and the other is called non-singular. There is another description of the singularity versus non-singularity is that when you write down the matrix which you can use to actually go to the real space from the momentum space, okay, it turns out that the matrix becomes singular, okay, it admits a zero eigenvalue, so to say, the determinant is 0 for the matrix. That is why we call one class of flat bands to be singular flat bands and the other class of flat bands to be non-singular flat bands, and when you have that singularity, the compact localization for all the states are not possible. Okay. Okay. So what we now ask is that what happens if you now place these systems to a magnetic field, to a uniform magnetic field, homogeneous magnetic field to start with. Okay. Okay, so you roughly expect what we may possibly get is that if you just have a flat band, an isolated flat band from the rest of the spectrum, practically nothing happens. Okay. You may have levels like Landau levels, these are all degenerate at the level of the flat band, and if you have a dispersive band on top of that, then you get the regular Landau level quantization. Okay. So for example, this is what happens exactly for a non-singular flat band. So for a non-singular flat band, what you get is that if you look at the Landau level quantizations, you will find that there are regular Landau levels on top of the flat band where I have set the flat band to be at 0 energy. Okay. So for my entire talk, I will talk about flat band at 0 energy, but you can trivially shift the flat band. Okay. So for this flat band, you will have Landau levels which are regular Landau levels, and if you zoom in around the flat band energy, you will basically have no splitting. Okay. But now the situation is very different when you look at the singular flat bands. Okay. It turns out that for singular flat bands, you do have the regular Landau level like scaling, which is Landau level like scaling, which are coming from the parabolic band, the parabolic dispersion. But even though your flat band is at 0 energy, when you calculate the Landau levels, you find additional Landau levels below the flat bands. Okay. So this is the region in the energy space for which in the dispersion there was no state available. So possibly then you can ask the question, and okay, maybe I will just and also it turns out that these kind of the Landau levels that you find in the region above the flat bands, they satisfy the usual scaling. Okay. However, the Landau levels that are below the flat bands have a very unusual scaling which goes as e to the -1/n. So if you remember the kind of scaling that I initially showed to you, that for any dispersions k to the b, the Landau levels goes as n to the b/2, but b is positive. For the anomalous Landau levels, it turns out that this exponent is negative. Okay. Okay. So then we ask the question that of course these are populating the region in the energy space for which there is no dispersive bands. That means probably the parameters of the dispersions are not influencing the formation of these Landau levels. And if these are not the parameters of the dispersions, then we ask that what is the parameter that is essentially giving rise to the genesis of this anomalous Landau level. Okay. So it turns out that the actual the culprit of behind this game is something called quantum geometry. Okay? It is something which actually occurred in many branches of physics, giving rise to many interesting phenomena. So here also it turns out this additional geometric information is very much required to understand this kind of anomalous quantization. Okay, so what is the quantum geometry that I am referring to here? I think everyone who studies quantum geometry in some context or the other, we'll probably start from something called a quantum geometric tensor. I'm not going into the details of that in the interest of time, but you can basically write down this tensorial quantity, okay, which essentially explain the parallel transport of Bloch states. Now from the quantum geometric tensor, you can formulate something called a quantum metric by looking at the real part of the quantum geometric tensor, while the imaginary part gives rise to the Berry curvature. And from the real part of this thing, from the quantum matrix, I can define something which is called the Hilbert-Smith distance. So it's a distance between two Bloch states. Okay. So it turns out that the kind of anomalous Landau level quantization that I have here, that I showed to you, E goes as minus 1 over n. If I want to compute the prefactor of that, it turns out to be the maximum of this quantum distance. Okay? So here is the prefactor, that is when this is non-zero, you will have a spreading of these, you will have this anomalous spreading of the Landau levels below the flat band. Okay, good. So for, because I will be restricted to quadratic band touchings, the parabolic band touchings. So it turns out that whenever you have Hamiltonian describing this quadratic band touchings, which you can cast in this form, okay, in the polar coordinates, then you can also define this Dmax by just looking at the quantum metric in the polar coordinate. Okay, there is a very simple cancellation for which only the polar coordinate survives, and from that you can calculate the maximum of the geodesic distance. Okay. Okay, so that is what it turns out. Then it turns out that when you have finite quantum distance, it basically implies that there will be band mixing between the Landau levels of the dispersive band and the Landau level of the flat bands, and the coupling between them is dictated by what is this called this quantum distance, and because of that you are getting level repulsion and you are seeing the appearance of Landau levels below the flat band energy. Okay, so I think I have talked enough about the phenomena. It's good to actually revisit what model can possibly give rise to whatever I just discussed. I will directly give you the glimpse of the model. This is what I call the minimal model to understand the kind of anomalous Landau level that I just described. Okay, so it's a two-band model, which describes a quadratic dispersive band or a parabolic band and a flat band. Okay, where I have set the flat band at E equal to 0. So I have, you will have certain number of parameters to describe a two-level Hamiltonian. From that I have imposed constraints, okay, including one, that the determinant of my Hamiltonian is 0 for all k. And it turns out that the whole model reduces to a 4-parameter model. So in order to understand the anomalous Landau level with a tunable quantum geometry, I need it's sufficient to look at a 4-parameter two-band Hamiltonian. Okay, what are the parameters here? The parameters of the Hamiltonians are A1, A2, A3 and A4. Okay, some of them have to be non-zero in order to see these anomalous levels, but importantly, these parameters, the way they enter in this Hamiltonian description, these A3 and A4 are two important parameters. You can set A2 to be 0 also. That gives you the distance. Okay? The distance if you tune A4 over A3, or the ratio of A3 and A4, you basically get a tunable quantum geometry. So if you place this model to magnetic field, the outer plane magnetic field, you can calculate it's a tedious calculation that Shojano basically did, that you can directly solve the Schrodinger equations, fortunately, and you will see that you will get a tower of Landau levels below the flat band, which goes like this. So there's a factor of 1 over 2n plus 3, so in the large n limit you have 1 over n, and the rest of the factor you can basically connect it to the quantum geometry of this problem, the distance of this problem, which will basically be a function of A3 and A4 when A2 is 0. Okay. So what I get basically is that I have anomalous Landau levels coming from these Hamiltonian. In the presence of a uniform magnetic field, I have these tower of anomalous states, which goes as Dmax square over n. Okay, good. So now what we ask is that what happens if you, instead of a uniform magnetic field, now that we have understood the formation of the anomalous levels, we ask that what happens if you, instead of uniform magnetic field, you apply non-uniform magnetic fields. Now, of course, the problem in its full generality is very difficult to solve. Okay, if I do not give you any particular flux profile, I do not know how to solve this problem. So, for that we start from a very simple starting point. Okay, and I am sure one can actually generalize this systematically. Okay. So, what is the starting point? From the continuum descriptions, I go to the lattice. Okay. So, I go to a lattice in which I know that I have a singular flat band. Okay. And one of the best examples is Kagome, okay, that I showed you in the very beginning. So, if you look at the spectrum of the Kagome, you have a flat band, and that flat band is actually the gapless flat band, and that flat band is actually a singular flat band. Okay. Good. So, I go back to my Kagome lattice and I propose the following flux profile. Okay. So, you can see that I have two parameters. One is alpha that controls the flux density, and there is another parameter which is called xi. That's actually the more important parameter, which controls the distribution of the flux within these structural unit cell of the Kagome. Okay. So, what's happening here? So, if your xi is 1, then you will see that you have proportionate flux in the hexagon as the triangles. So, it's a uniform flux configurations where the flux through the hexagon is 6 times the flux through the triangle. Okay. And you can tune xi away from 1, you can go all the way to 0 or even more than that when you are playing with the flux distributions within the Kagome triangles and the Kagome hexagons. Okay. So, with that I will go on, I will form the magnetic supercell by fixing alpha. You can take that to be some p over q with p q coprimes, and you can solve the anomalous Landau level spectrum. Now, what we find is very interesting is that, see, at xi equal to 1, when you have uniform Landau levels, uniform magnetic fluxes, you have this beautiful tower of anomalous Landau levels here. But as you tune xi from, okay, so I will be very fast. Okay. So, as you tune from xi equal to 1, you see that there is a gradual collapse of the Landau levels. Okay. So, all these anomalous Landau levels are essentially collapsing when you add inhomogeneity in the fluxes. Okay. So, at each point you can actually very clearly see the scaling, and maybe I can be a bit more faster. It turns out that the scaling with respect to xi turns out to be roughly linear. So, if you remember the kind of scaling that I showed to you, that E square goes as d max square over n, that is sort of replaced by a xi. So, apparently the flux inhomogeneity parameter is playing the role of a quantum distance, some imagined quantum distance in the problem. Okay. Good. So, what I find here that I have a special point xi equal to 0 at which you have massively degenerate Landau levels. So, you can literally solve the Hofstadter problem or the full tight bending problem. You will see there are degenerate flat bands in the system. We are yet to understand the nature of those flat bands, but maybe I should go a bit fast. That there is a very intriguing supersymmetric connection to understand the degenerate Landau levels at 0 energy. For those who want to go details, this is the fundamental algebra that goes into these calculations. I am not again giving details of that. The upshot is that this turns out to be a very nice lattice analog of something which is called this Aronoff-Kashert theorem. Okay, it counts the number of nodes, number of zero modes in inhomogeneous fluxes. So, we found sort of a lattice analog of that very old theorem. There is a partial Aronoff-Bohm caging in this system because you have a magnetic flat band, and you have degenerate flat bands for which you can actually construct compact localized states in the presence of the magnetic field. Okay. So, and these kind of flat bands are sort of robust to many hopping and flux disorder in the system. Okay. Maybe okay. These are the response. You can look at the quantum Hall response of these anomalous Landau levels. You will see these are very close to the original Landau levels, contributing to Chern number plus minus 1 with a very sort of uniform Berry curvature, etc. Maybe I should go to the. Oops. Okay. This is the last slide of my talk, but I want to conclude it. So, what we are now trying to do is that what are the sort of engineerable quantum platforms in which we can see these effects, and we have actually found that certain protocol in optical lattice based model where it is possible to actually see the tower of anomalous Landau levels when you look at the Bragg scattering. Okay. And we also want to understand the kind of quantum oscillations that you can possibly expect from these kind of gapless flat bands in terms of these anomalous Landau levels. Yeah, I think I would like to stop here. Thank you.
So suppose a system has a flat band. Is there a procedure or a way by which you can construct a compact localized state, like construct Vanier orbitals and all?
Yeah, that is there. I mean, if you have a flat band, then from the flat band, the way I showed to you actually, you just calculate the block eigenvector corresponding to the flat band states, and then from that you just do an inverse Fourier transformations. Oops, I think I was too fast. Yeah. Okay. So if you find that your the block eigenvector, the entries of the block eigenvectors, if it turns out to be a finite sum of block phases, then when you do this inverse Fourier transformation, you will see that only certain C n A L will be non-zero, and the rest of them will be zero. So that is what we call as the compact localized states.
Also, if you have a band which is flat in a particular direction but dispersive in other direction.
Yeah, that's a very good question.
Can you like get a partial compact?
We have tried that, but I do not have a very conclusive answer to that. I think compact localizations in this form will not survive, but there will be some dispersion of the compact localization.
Okay. Would it be that it's dispersive in one direction, look like?
Well, that you can do anyway, even if you have a flat band. See, when you have a singular flat band and you look at the compact localized states corresponding to the flat band, you will see some of the states are actually extended. It's only compact along the perpendicular directions. Sure, sure. Yeah, sure. So, the phenomena of Aharonov-Bohm caging is that in certain lattice models, when you apply some particular pattern of some particular value of uniform fluxes, when you apply certain types of fluxes, uniform fluxes, it turns out that all the bands can be flat for the magnetic supercell. And it turns out that in the presence of the magnetic field, you have a structure which is very similar to this compact localized states. If you look at the electronic wave functions, you will see that the structure of the electronic wave function will be suggestive of the fact that the electrons cannot leak beyond certain cluster. Yeah, so that is what we call Aharonov-Bohm caging, and what we are having here is a partial Aharonov-Bohm caging in the sense that not all of the bands are flat here. So for us only the lowest band is flat. However, we do not need a uniform flux also. It's a non-uniform flux, and the trade-off is that you are only the lowest band is flat.
So you say your lambda levels are flat in wave vector, I mean in K. So will you get any conductivity?
Well, they are not fully flat in that sense. If you calculate, so there are this dispersion. So in lattice, you generally do not have exact flat Landau levels, something analogous to the Landau levels.
In real materials, you will get disorders or something.
Yeah, that I have not explicitly included here, the kind of phenomena that goes into the formation of quantum Hall effect and the way you get plateaus, etc. But modulo that, if you just calculate the Kubo formula, the Hall conductivity using Kubo formula, sum over all the K states, you get reasonable quantizations in the conductivity.
Okay. And also you say that anomalous Landau level, so I mean that is zero magnetic field. The Landau levels are in zero magnetic field.
No, the Landau levels are in finite magnetic field.
So what do you mean by anomalous?
The term, the reason I use it anomalous, because the quantizations of the quantizations is Bohr atom, where you have 1 over n squared scaling.
Okay, thank
Where?
So in parameterizing D0, D1 and D2, so you have used four parameters like A1, A2, A3. I mean, why 4 parameters is needed?
Yeah, it's a very good question. I will try to be very brief. If you do not understand, you can catch me later, okay? I want to write down a 2-band Hamiltonian, generic 2-band Hamiltonian with D0, D1, D2, D3, okay? These are quadratic polynomials. So each of them will admit 3 independent parameters. So to start with, I have 12 independent parameters, okay? You can trivially rule out 3 independent parameters by rotating your coordinate system suitably. So a 9 parameter system is sufficient to explain a generic 2-band Hamiltonian, okay? Now I have a condition that my flat band is at 0. So my determinant of the Hamiltonian has to be 0, okay? So it's a quartic polynomial that fixes 5 coefficients out of 9. So it removes 5, so you are left with 4 parameters.
So before we are late, just I wanted to ask, is it just sufficient to have only the flat band, or just you also need some dispersion?
Oh, you have a gapless flat band, so you have dispersion and a flat band.
So
An isolated flat band will show you nothing.
only the flat band is not.
Yeah, no, an isolated flat band will not give you anything.
So okay, let's again thank the speaker with round of applause.
Should I just close it or?